Set of exponentials. Drag all the functions that model exponential decay into the box. All right, let's go back to exponentials. Exponentials look something like y is equal to c a to the x power. Right? Sorry. Y is equal to c times a to the x power. Now, what does this c do? The c is the y-intercept. Yes, it is. Wait, is it the y-intercept? Yes, it is the y-intercept. C is the starting point. That's the gummy bear factor. Remember how I had this big hissy fit about why I originally called this A, but they called this C, and I didn't like that and all of that kind of stuff. Remember? I was getting into all of that. And that's because in every other equation, this was an A. And that A was your stretchiness factor. But this time they call it C and whatever. Let's just deal with it. It's that. And then this A right here, this told us a few things. This told us the growth rate, exactly. So if A were like 2 to the x power, if I were to graph 2 to the x power, it would look like exponential growth, like this. We cool? Now, if A were 1/2, then if I were to make a table, if x is equal to 1, y is equal to 1/2. If x is equal to 2, y is equal to 1/4. If x is equal to 3, y is equal to 1/8. Or, yeah, 1/8. And so on and so forth. It would kind of be a graph that looks like this. Right? Exponential growth looks like this. Exponential decay looks like that. And what is it about A that will tell me whether or not I'm dealing with decay or not? Can you tell me? Like, why did 1/2 give us decay? Ah, there we go. It was a fraction, or it's some number less than 1. I agree with Lucas. So let's look at the questions that they have. Which of these functions, and I'm looking at number 22 on that PDF you guys talked about, which of these functions has an a value less than 1? Yes, I agree with you. An a value greater than 1 would be called exponential growth. An a value less than 1 would be exponential decay. So that the first one, y equals 0.99 to the x power, that's exponential decay. The next one, y is equal to 0.86 to the x over 0.3. I'll be honest with you, that 0.3 doesn't really make much of a difference. It's still exponential decay. What if a is a negative number? No. If a is a negative number, then what happens is something extremely freaky. I think what happens is it doesn't flip over the x-axis. What happens, I think, is it alternates back and forth in a weird way. I'll show you an example of that. But for now, in all of the options that you're given, there isn't any negative a values here, so you don't have to worry about that. So all you got to do is choose all of the ones that have an a value that is less than 1. So it's this one, the middle one, and that's it. Just those 3. All the other ones, the 1.07 and 1.01 and 1.02 and 1.27, those have a values that are bigger than 1, so those represent exponential growth, not exponential decay.
So all the numbers in the parentheses is A.
Yes, the numbers in the parentheses is A. Now, let me just, so we're done with the problem. There it is. That's the answer. It's that easy. Cool. To answer to answer Sophia's question, what happens if a is negative? Let's try that. Negative 2 to the x power. Let's make a table. Oh, I'm sorry, fx. And I'm telling you now, it's freaky. I'm wondering. Yeah, I'd love to go over an absolute value problem. I'll tell you all about an absolute value problem that's really funny, actually. All right, never mind. All right. Let me. If x were 0, this is 1. Right? Because negative 2 to the 1 power, or the 0 power is 1. Cool? If this is 1, this is negative 2. If this is 2, this is positive 4. Because negative 2 squared is positive 4. If this is 3, this is actually negative 8. Do you guys see something freaky that's happening? What does it even look like? I'm wondering what Desmos says, but I have a feeling that it looks like this. Or something like that. Let's Desmos that sucker. I'm not sharing my screen, but you guys can go into Desmos and type in the negative 2 to the x power. Let's see what it says. I can tell you where I think I've seen this thing before. Let's see, negative 2 to the x power. Desmos couldn't figure out what I'm trying to do. What about positive 2 to the x power? Oh, so it knows what to do with that, but it doesn't know how to do negative 2 to the x power. Why doesn't it not know how to do that? Negative 2. I'm trying Wolfram now. Yeah, that's exactly what I thought it would look like, right? Okay. Here's what I'm thinking is, oh, it does know, it just worked for me. Oh, well, mine didn't work. Desmos didn't know how to do it. Anyway, yeah, it looks exactly like what I did. Here's one of the things I think that this would be useful in, is you guys ever hear of a feedback loop? Sophia, you're a musician, right? So do you play music? Oh, what do you play?
Bass and guitar.
You're a bass player? I love bass. I got a 5-string Yamaha RBX bass. I actually love slap bass. It's so cool. And you play guitar?
Yeah.
Oh, you're so cool. All right. Anyway, you ever go up on stage?
I played at Hard Rock Cafe.
Really?
Yeah.
Wow. All right. So you have your microphone. It's an ugly microphone. There. You have your microphone, and you got your speaker over here.
Oh, and
You ever point your speaker at the microphone?
hurts.
And so what's happening is you speak into the microphone, and then that microphone sends the signal into the speaker, and then it amplifies it a little bit. So now a louder sound is coming back into the microphone. And so then that bigger sound comes back into the speaker, which gets amplified again. And then right? It just kind of goes out of control, right?
Are you talking about like when you point the microphone to the speaker?
Mhm.
Yeah.
That's feedback loop. That is kind of the description of what Sophia just described, right? Because it's a sine wave that's getting louder and louder and louder as it goes on. In fact, the crazy thing is, you know, this exponential growth, exponential decay, and all of that kind of stuff, that has everything to do with music. So now you guys are wondering, why the hell did I learn about exponential growth? Well, let me tell you about exponential growth and exponential decay, because it's actually pretty darn cool. All right, anyway. That's how you do that one. The problem, actually, 22 is really easy. You just have to understand the properties of the exponential function. Anyway.